morning, grade 8 learners. Welcome to Grade 8 Science Valenzuela Live, where learning science is fun and exciting. I am Sir B at your service from Vicente P. Trinidad National High School. In this session, we will be talking about electron configuration. At the end of discussing this topic, we should be able to use a periodic table to predict the chemical behavior of an element. For this session, we will do the following. First, we shall define electron configuration. Second, we shall identify the different parts of an electron configuration. Lastly, we shall write the electron configuration of a given element using electron distribution mnemonics. Also, make sure that you prepared the following materials: your pen, your notebook, your module in science, and your periodic table. Let's get started! Have you ever wondered why there are some pair of substances that cannot join together, just like oil and water? It is because these substances are composed of different kinds of atoms with different kinds of arrangement. These properties will determine what type of chemical reaction the substances can participate in. For us to easily describe the properties of a substance during a chemical reaction, we must understand first the properties of an atom. The most active particle during a chemical reaction is the negatively charged particle called electrons. During a chemical reaction, electrons may be lost or gained from an atom. Currently, one of the widely accepted atomic models is the quantum mechanical model. In this model, the atom is composed of two main parts: an atomic nucleus, where protons and neutrons are located and it is found at the center, and an electron cloud, a region where electrons are located. Also, through this model, we derive equations to characterize the behavior of the electrons in an atom. This led to the formulation of quantum numbers, a set of 4 quantum numbers that were used to describe different atomic orbitals. An atomic orbital is a region of probability where an electron can be found. Now, the question is it possible that we can determine the exact location and velocity of an electron? Currently, it is not possible because, according to Werner Heisenberg in his Heisenberg's uncertainty principle, the position and velocity of an electron cannot both be measured exactly at the same time, even in theory. So for now, what is essential for us to learn is about atomic orbitals and how electrons were distributed in these orbitals. An atomic orbital is a region of probability where an electron can be found. Again, the term probability is included in this definition because of what we have learned about Heisenberg's uncertainty principle. We will now focus on 4 kinds of orbitals. These orbitals, the S, P, D, and F orbitals. These orbitals have different shapes and they look like this. It is important to remember that these shapes do not represent the actual shape of an electron. These shapes describe regions where an electron can probably be found. Each orbital can handle up to 2 electrons. This means that more orbitals are needed if an atom has more electrons. A while ago, I mentioned that these orbitals can be described using quantum numbers. Let's talk about them. The first quantum number is the principal quantum number, or n, which can have any positive integer value 1, 2, 3, 4, 5, 6, 7. This quantum number represents the energy level of an electron. Each orbital has an n value. The higher the n value, the farther the orbital is from the atomic nucleus. The second quantum number is the angular momentum quantum number L, which can have an value or any value from 0 to n minus 1. For example, if an electron has an n value of 2, it can have an L value of either 0 or 1, because 2 minus 1 is equals to 1. This quantum number describes the shape of the orbital. Now, let's take a look at the different orbital shapes and their respective quantum numbers. If L is equals to 0, it describes S orbital, which is spherical, 1 for each energy level. If L is equals to 1, it describes P orbitals, which are composed of lobes that extend outward on 3 axes, 3 for each energy level. If L is equals to 2, it describes B orbitals, which looks like this, 5 for each energy level. And if L is equals to 3, it describes F orbitals, which looks like this, 7 for each energy level. The third quantum number is the magnetic quantum number, or M sub L, which can have any value from negative L to positive L. For example, if an electron has an L value of 3, it can have an M sub L value of negative 3, negative 2, negative 1, 0, 1, 2, and 3. This quantum number describes the number of orbitals there are for a type of energy level, and it also describes a specific orbital among a particular set. Lastly, we have the fourth quantum number, and it is the magnetic spin quantum number, or M sub S, which can have a value of either 1/2 or negative 1/2. This quantum number describes the spin of an electron inside an orbital. These quantum numbers signify each other, or each electron has these quantum numbers signify that each electron has a unique set of 4 quantum numbers. No 2 electrons in an atom having the same set of 4 quantum numbers. This is stated in Pauli's exclusion principle. In an atom, no 2 electrons can have the same 4 electronic quantum numbers. Now, let's use this knowledge of quantum numbers for us to further understand the use of electron configuration. An electron configuration is the arrangement of electrons in energy levels around an atomic nucleus. It can be described using a notation as shown in this example. The number on the left side represents the principal quantum number, n, or the energy level. The letter in the middle represents the sublevels. It can either be S, P, D, or F. Now, S sublevel has 1 orbital, so it can have up to 2 electrons. On the other hand, P sublevel has 3 orbitals, so it can have up to 6 electrons. D sublevel has 5 orbitals, so it can have up to 10 electrons. And F sublevel has 7 orbitals, so it can have up to 14 electrons. The superscript on the right of the electron configuration notation is representing the number of electrons that the sublevel currently has. Now, how can we determine the electron configuration of an element? We can use several mnemonic devices to help us. One of these devices is called the chemistry model. Let's break out our notebooks and let's draw the chemistry model here. Okay, follow my instructions. Okay, first, write the numbers 1 to 7 on the left side. Okay, on the left side, just as shown in the board. Make sure that you leave 1 to 2 spaces between each number so that your mnemonic device will be readable. Now, these numbers 1 to 7 shall represent the s orbitals. So, write letter S beside them. So, you're going to have 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Next, write numbers 2 to 7 on the opposite side. Just like this. These numbers shall represent the p orbitals. So, write letter P beside them. So for that, you're going to have 2p, 3p, 4p, 5p, 6p, and 7p. Next, write numbers 3 to 6 on the right side, okay? On the inner right side, just like this. These numbers shall represent the d orbitals. So write letter D beside them. You're going to have 3d, 4d, 5d, and 6d. Finally, write the numbers 4 to 5 on the inner left side, just like this. These numbers shall represent the f orbitals. So write letter F beside them. You're going to have 4f, 5f, 6f, and 7f. The last step is you are going to draw several arrows. Now, follow how the arrows were drawn in this figure. So, let's trace the pathway of these arrows. So, you have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, and 7p. There we go. We now have our own chemistry model written in our notebooks. This is a mnemonic device that can be used or we can use to determine the electron configuration of an element. Now, this chemistry model that we constructed a while ago actually follows off-bound principle. In distributing electrons, we must follow the guidance stated in the off-bound principle. It is stated that in the ground state of an atom or ion, electrons fill atomic orbitals of the lowest available energy level before occupying the higher energy levels. Therefore, if we are going to follow off-bound principle, the first orbital to be filled with electrons shall be 1s, followed by 2s, then 2p, then 3s, then so on. So, in this chemistry model, we are actually tracing the correct order of the distribution of elements in these atomic orbitals. Now, let us practice writing an electron configuration using this example. what is the electron configuration of oxygen? Now, for us to determine its configuration, we must identify first the number of electrons of a neutral oxygen atom. Now, how many electrons does an oxygen atom have? Since oxygen has atomic number 8, it has 8 protons and 8 electrons. This means that we are going to distribute 8 electrons to the different orbitals. Now, going back to your chemistry model that you made in your notebook, which orbital is the first to be filled with electrons? If you answered 1s orbital, you got it correctly. We shall fill 1s orbital with 2 electrons. So we are going to have 1s2. So therefore, we only have 6 electrons of oxygen remaining. Now, where should we put the electrons next? In which orbital? Correct. We will place them in 2s orbital. Again, 2s orbital can only have 2 electrons. Therefore, you will have 2s2 as the next part of the configuration of oxygen atom. This means that there are 4 electrons left to be distributed. Which orbitals shall they be placed next? Right. They will be placed at 2p orbital. So the electron configuration of oxygen is 1s2, 2s2, and 2p4. Now, let's try if you can do this on your own. What is the electron configuration of chlorine having an atomic number of 17? Write your answers in your notebook. Recall what we are going to do for us to identify the electron configuration of a specific element. So you are going to base your correct sequence of placing electrons into their orbitals using the chemistry model, which follows the Aufbau principle. Okay? Let's see if your answers are correct. The correct configuration of the atom chlorine is 1s2, 2s2, 2p6, 3s2, and 3p5. Now, what if an atom is too large? Will its electron configuration be as large as well? The correct answer is yes. Let's have an example. Germanium, having an atomic number of 32, has this configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p10, and 4p2. It's too long, right? But for a long configuration, we can shorten it with the use of 4 symbols based on noble gases. Now, this will form what we call a noble gas configuration. If we take a look at our periodic table, we can find the noble gases at the rightmost portion. Okay? The rightmost group of elements in your periodic table are composed of noble gases. A noble gas configuration of an atom consists of the element symbol of the last noble gas before the given element, and to be followed by the configuration of the remaining electrons. Now, going back to our sample element germanium, what noble gas comes before germanium? Take a look at your periodic table. Okay, read the elements backwards. From the higher atomic number to the lower atomic number, which element is it? Correct. The noble gas before germanium is argon. Okay, with atomic number 18. Now, we can substitute the configuration of argon into its element symbol. And what is the configuration of argon? 1s2, 2s2, 2p6, 3s2, and 3p6. We are going to substitute that configuration into the element symbol of argon, which is Ar. And we are going to place brackets outside of the symbol argon. Then, we will leave the remaining configuration as is. Therefore, the noble gas configuration of germanium is argon core, 3d10, 4s2, and 4p2. Or we can also write it like this. Okay? Argon core, 3d10, argon core, 4s2, 3d10, and 4p2. Now that you have learned a lot for this session, let's list the most important points. First, electron configuration is the arrangement of electrons in energy levels around an atomic nucleus. Electron configuration is composed of information such as energy level, sublevel, orbitals, and the number of electrons distributed in specific orbitals. And mnemonic devices, just like the chemistry model, can be used to easily determine electron configuration of an element. Now, let us test how much you have learned for our today's topic. You're going to write the electron configuration of the given or of the elements that I am going to give. Use your chemistry model, and you can also use your periodic table to follow the correct sequence of electron configuration. Are you ready? Then let's get started. Here is the first element. What is the electron configuration of lithium having atomic number 3? Write your answers in your notebooks. Remember which orbital shall be having the electrons first. Then what will be next? Okay, the correct configuration for the atom lithium is 1s2 and 2s1. Also, by using noble gas configuration, we can also write the configuration as helium core and 2s1. Okay, but both answers are correct. Now let's proceed to the next element. How about the electron configuration of neon? Write your answers in your notebook. Okay, take a look. What is the atomic number of neon? And then recall, what does that atomic number represent? Then using that number, how will you distribute the electrons to the specific orbitals? Okay, let's take a look at your answers. The correct configuration for neon is 1s2, 2s2, and 2p6. Now, using noble gas configuration, we can also write the configuration as this: helium core, 2s2, and 2p6. Let's now proceed to the third and last element. What is the configuration of the element silicon, having an atomic number 14? Okay. Make sure that you get the right order of the orbitals where the electrons shall be distributed. Let's see. The correct answer for the configuration of silicon is 1s2, 2s2, 2p6, 3s2, and 3p2. In short, neon core, 3s2, and 3p2. For those who got all of the answers correctly, good job. Keep up the good work. But for those who aren't, it's okay, no problem. Okay? It takes practice. But the good thing is we are trying. We continuously try to succeed in what we are doing. So go back to your modules, study, review your lessons, and hopefully we can do better in our next sessions. Now, if you have other questions that you want to ask regarding the lesson, feel free to ask me in the comment section. I will do my best to answer all of your questions. That ends our session. See you next week for another episode of Grade 8 Science Valenzuela Live. Stay safe and have a great day.